summer Urban Integrated Field Laboratory joint seminar series. I'm Christina Negri. I'm the lead PI for Crocus, and I have the pleasure to introduce the speakers today. The focus is going to be heat for this particular seminar, and we have two teams presenting. We will start with a 30-minute presentation from the SW-IFL presentation, seeing David Sailor and Alamin Molla. The title will be, for this joint presentation, will be using vehicle-based traverse measurements to explore temperature variations across Phoenix, a preliminary assessment. Then we will move on to another 30 minutes of presentation from BSEC with Darryn Waugh talking about observed heat in Baltimore, and Ali Eyni talking about equitable urban heat island reduction pathways under climate change. So I'm going to go ahead and introduce all the speakers, and so we have that, and then we'll move seamlessly across the presentation. We have left about 25 minutes for Q&A, so please hold on to your questions unless it's essential for any reason after the speakers have spoken. So Dr. David Sailor is the director of the School of Geographical Sciences and Urban Planning at Arizona State University and the lead on the Southwest Integrated Field Laboratory. His research focuses on the intersection of climate and the built environment, specifically in understanding the causes, effects, and potential solutions for mitigating extreme heat in cities. Alamin Molla, I hope I'm pronouncing your name decently, is a second-year PhD student in ASU Schools of Geographical Sciences and Urban Planning. He obtained a master's in geoinformatics and geospatial intelligence from George Mason University and worked with Drs. David Sailor and Dr. Flores, focusing on urban heat island, air quality, and environmental justice, utilizing cutting-edge GIS science, GeoAI, and remote sensing techniques. Moving to the BSEC team, Darryn Waugh is a professor in the Department of Earth and Planetary Sciences at the Johns Hopkins University. His primary research interests are large-scale atmospheric and oceanic flow and transport, with a focus on understanding global environmental issues such as stratospheric ozone depletion, climate change, and air quality. In recent years, his interests have expanded to include planetary atmospheres and urban climate. He is talking about, I was asked also to mention that he has no training or expertise in instruments and urban measurements, which is what he will be talking about as well. Ali Eyni is a PhD student in the Department of Earth and Planetary Sciences, working with Ben Zaitchik, and his general research focuses on the multi-criteria decision-making and dynamic adaptive pathways for urban adaptation. With that, I would like to give then the floor to Dave Sailor as the first speaker. And Dave and Alamin, I trust you will hand the presentation to each other and stay within the 30 minutes. Thank you.
We will do our best. So just a quick confirmation, you're seeing my PowerPoint slide?
Yes. Okay.
Yeah, so thanks, Christina. So I am Dave Sailor. I am the overall PI for the SW-IFL. And our project really has a lot of efforts going on related to heat, both observational, but also modeling, and also in terms of policy and planning interventions. But what I'm going to focus on today with Alamin is just a small subset of the work that we've done related to heat. In particular, this past summer, we just completed our big summer field campaign, and part of that campaign involved mobile observatories and measurements of heat in indoor settings. But part of that campaign also focused on measurements from these vehicle-based traverse systems. And so keeping in mind that this is all very new, we just got the data literally in the last few months. What we're going to present today is just an initial look at the data to give you a sense of where we're heading and what we're finding. So as Christina indicated, this is going to be a tag team presentation with myself, and I'll hand it off to Alamin in a little while. So jumping into presentation. So the heat results that we're going to share are going to focus on just air and surface temperature. So keeping in mind that thermal environments and heat more generally includes both an indoor and outdoor component. It includes a lot more than just air and surface temperatures. But since our measurement campaign had a very substantial effort measuring surface and air temperatures, we're going to focus on that. And we're going to focus around 3 specific questions. So the first question, if you think about it, at the core of our IFL, we're really focused on solutions. And so the first question is simply, we've designed our observational campaigns to explore to what extent do neighborhood scale cooling interventions affect local and downwind air temperatures. So we're going to look at 3 specific interventions from our observational data set: cool paving, urban water bodies, and urban parks. And then as we consider using models to project the impacts over time of large-scale implementation of these interventions, we need to better understand the subgrid variability of thermal environments. So we're also interested in the question, what is the intra-neighborhood variability of air temperatures, and how does it compare to citywide variability? So that's really integral in terms of our ability to use modeling results to help identify, if you will, hotspots and so forth. And finally, on that topic, many researchers tend to rely on easily obtained satellite-based land surface temperature, or LST data, as a measure of urban heat or urban heat islands, and identify urban hotspots. And we want to recognize that human exposure to extreme heat, depends very much on air temperatures, not just surface temperatures. And so we seek to better understand whether or when land surface temperature, or LST, is a useful indicator of thermal environments by asking, under what conditions do surface temperatures correlate well with local air temperatures. So all of the observations that we're going to discuss today, again, focus around one specific measurement system that we had from this field campaign this summer. And we'll be presenting some of the early results that we had from observations back in summer 2023 as well. So the traverse methods revolve around a set of instruments that we mount on vehicles to measure both 2-meter air temperature, surface temperature. Vehicles drive on roads, this is road surface temperatures, and vehicle location. Last summer, we were sampling every second. This summer, we backed off to sample every 2 seconds to allow instruments to be in the field for a much longer period of time without needing to be downloaded. And these sensors are actually an evolution, if you will, of an approach that we first introduced back in 2006 to 2008 through some measurements focused on trying to understand the spatial variation of urban heat and linking that to spatial variation in land surface characteristics. So the traverse systems themselves, as I said, they have 3 components. One is a simple GPS tracker. It's accurate to approximately less than 2.5 meters, and that was sampling every second. And then the air temperature sensor was a 4-wire fast response RTD sensor, so very high accuracy sensor and logger system that was mounted at 2-meter height, shaded from direct solar exposure and aspirated by the vehicle motion. So we're able to actually filter out low vehicle speeds, so we're not biasing our results. That sensor was sampling every 2 seconds, and then ground surface temperature was using a fast response IR sensor and logger that was also recording at 2 seconds, and then we match the timestamps of the 3 sensor systems automatically in software, so that we're able to create a package of data that includes air surface temperatures and GPS location every 2 seconds. So starting with our first question, I'll talk a bit about our initial results and looking at the effects of cool paving, and then I'll hand it off to Alamin, who's going to discuss urban parks, water bodies, and then also the remaining 2 questions. So this is a map showing the extent of our traverse campaigns, which included a group of K through 12 teachers that we recruited to help with these measurements, as well as faculty, staff, and students at ASU. And part of Katja Lamer's team from Brookhaven, who actually came to Phoenix for the summer field campaign in 2024, she was making a wide array of measurements at the surface and scanning through the atmosphere with her mobile observatories. We're not going to be presenting any of those results here today. We do have a very extensive set of observations now, though, taken over a 2-month period, both in the summer of 2023 and a better data set, more complete data set for summer 2024. So this map just shows some of the locations of these different traverses across the Phoenix metro area. And the specific locations of the measurements that we're going to discuss today are for these 3 locations: the Desert Ridge Marketplace, which is a cool paving demonstration site; the Dobson Ranch, which is an urban park site, if you will. It's a golf course, essentially; and the Lakes community, a neighborhood with a network of man-made lakes. So let me start with Desert Ridge Shopping Center. It's a shopping center in North Phoenix. And this is a view from Google. I just extracted from Google a few days ago, showing the site, which has a very large area of surface parking with an extensive amount of course, asphalt, black asphalt. And as with any asphalt parking lot, these parking lots need to be periodically resealed. And it's very common to reseal a parking lot, say, every 3 to 5 years. And so we took advantage of this natural cycle in pavement refurbishment to conduct a test bed study of cool paving. So cool paving is simply an asphalt-based product that you apply to the surface of the paving. So it's a very thin layer that goes on top of the asphalt. It fills cracks, and it basically gives the asphalt a longer life. And you need to do this every 3 to 5 years anyway. The traditional approach is with a black topping asphalt-based product that turns that surface pitch black. And so the experiment was actually conducted over, you can see this little green box here is a 63,000 square foot area coated with a cool paving with a solar reflectance of about 0.28 initially. And at the same time, they resurfaced the entire parking lot over the span of about a month. And since they're using a dark seal, the conventional sealant, it has a solar reflectance of only 4%. So 4% compared with 28%. So a very big difference initially. And I should note that over time, any light surface tends to get darker over time. Any dark surface tends to get lighter over time. At least that's true with asphalts in particular. And so we measured both the subsurface, surface, and near surface air temperatures. We used a wide array of instruments. So we flew an infrared camera in a helicopter to help get sort of large scale visual of the site. We can actually quantify the surface temperature from that. But most of our surface temperature measurements were focused on measurements from our mobile car vehicle traverse, which included air temperature at 2 meters, but it also, in this instance, we had not just the surface temperature with an IR sensor, but we also had air temperature at about 25 centimeters, 50 centimeters, and 1 meter. So we had a rake of air temperature sensors to give us a sense of the spatial variation away from the surface. We also, this is me in the left-hand bottom corner, taking some solar reflectance and thermal emittance measurements. And we did that over time over the past year, so we could actually track how the characteristics evolved. We buried some sensors underneath the pavement before they resealed it so that we could track subsurface temperatures. This is them helping us install those sensors. We had a network of 4 weather stations just for reference weather data, two stations in the cool surfaced area, 2 stations in the darker surface area. And then, of course, most of our measurements focused on data obtained from the vehicle traverse. So the cool paving results, just very quickly, we did see a degradation in the solar reflectance over time. So a cool surface starts out very reflective. In this case, it's about 28%. And then after about a year, it decreased to a solar reflectance of about 0.21. So it's just a sampling of a number of locations in the parking lot. Whereas the dark seal, actually, as it wears, it gets a little bit lighter because it starts out so dark that any dirtying of the surface tends to actually brighten it up a little bit. So it went from 4% to 4.3% reflectance. And so the measurements I'm just going to summarize very quickly here are for a typical summer afternoon. So we do have extensive data over a large period of time. But if you look at the surface temperature, we found that that's about 8 degrees C lower than the conventional dark paving. So this little graphic in the bottom that shows this dark red area and then this green area, those are just highlights showing where the traverse measurements were made. And so this happens to be a sampling of data from 2 p.m. on a September day back in 2023, shortly after the cool paving was installed. Every one of these dots is actually a measurement point from a vehicle. We had 2 vehicles traversing both areas over a 15-minute period. And so we're able to see up to an 8-degree reduction in surface temperature. The subsurface temperature, as measured by those buried sensors, we saw a reduction on average of 2 degrees C and as much as 4 degrees C reduction in mid-afternoon. So that really speaks to the stored thermal energy in the asphalt, which of course is very important for the evening hours as that stored energy comes out into the airshed. And the air temperatures, as we measured it from about 0.5 to 2 meters, sort of in the living space of people in the parking lot and downwind, we measured to be almost 1 degree C reduction in air temperature. And so we see this as a very compelling set of results, suggesting that cool paving has significant benefits in terms of reducing stored energy, reducing surface temperatures, and reducing air temperatures. And now I'll go ahead and hand it off to Alamin, who's going to discuss other aspects of our initial analysis of the summer's data. Alamin, just say next slide when you want me to advance it.
Yeah, thank you so much, Dr. Sailor, for giving me the floor to talk about our research. Dobson Ranch area is one of our study sites where we have taken extensive measurement in the summer to actually see the downwind cooling effect from the urban vegetated area, that's been the urban parks. Next, please. So from our initial investigation, we can see that from the upwind and the downwind direction, and there is about 1 degree Celsius downwind cooling effect based on this on-traverse measurement. And I would like to emphasize that this is just based on our initial assessment on the single day and single time, but we have a large amount of data for every single site. So we are aiming to make a very systematic investigation as we move forward with our research. Next, please. This is our another site. It's the Lakes community, which is actually the neighborhood built around the intensive system of artificial lakes, which is basically for aesthetic purposes, but it also has the potential for cooling effect in the neighborhood of the water bodies. Next, please. So if you see here in the Lakes community, there is around 1.1 degrees Celsius downwind cooling effect in the around 11 a.m. That's the late morning time. Next, please. And like existing literature actually suggests that the water bodies in the daytime, it actually has the cooling effect since it actually absorbs the heat, and in the nighttime, it actually can reverse that. So we also wanted to have some kind of initial insight on how is actually that happening in our study site. And then we, next please, here we actually see that in the evening time, if you see the orange mark area, it is kind of, the warmer side. So we can actually, that is our initial assessment that this area is kind of a warmer, even if you compare the downwind and the cooling wind effect, that is only about 0.25 degrees Celsius if we compare these both areas. Next, please. And then now, we all the like the existing atmospheric modeling and the other model mostly usually focus on the kilometer or more than kilometer areas. But now we want to investigate that how the temperature within this, I mean, the sub-kilometer area can actually differ that. And if we, I mean, with our traverse measurement, we can actually have some kind of better insight on the local variation of the air temperature. Next, please. Yeah, we have numerous, I mean, based on our traverse measurement, numerous examples where we have seen that there are temperature variation around 2 to 3 degrees Celsius in less than 100 meter. For example, you can see this in this area. It's around in the late morning. You can see less than 100 meter distance. There is around greater than 2 degrees Celsius air temperature differences. Next slide, please. This is another example where you can see in the left-hand area, this is the mobile home parks, and the right side is kind of the cooler area, that is the single home housing unit. And within this 100-meter distance, there is around 2.5 degrees Celsius temperature differences. And all this measurement have been taken in within 15 minutes. So one of the region, I mean, if you see in the images, the coverage of the asphalt and the other impervious surfaces kind of higher in the left areas, that's the mobile home parks. So that is one of the region why the temperature we have, it appeared to have a temperature difference between these two sites. Next, please. And then like we have conducted traverse measurement in the multiple sites, but it's very unlikely like we will be able to do the traverse measurement for every areas within a city. For example, in the Maricopa County is a huge large area, but we can use this traverse measurement as a training data, and we can deploy our machine learning model to train our model and make the prediction for the whole study area. Next, please. For this study, we used extreme gradient boosting, the supervised machine learning model, to train our model based on the traverse measurement data around 2 p.m. that we have gathered in the last summer, 2023. And we have used other covariates which have supported by the previous literature to make the prediction. We have used land surface temperature, elevation, canopy coverage as height, since we are working on the air temperature, not the surface temperature alone. And then several NLCD land cover categories, such as for developed areas, water bodies, and the cultivated crops. And then we did intensive hyperparameter tuning to make the accuracy for our model have a good prediction for our model. Next, please. This is the 12th site. We have gathered the air temperature measurement, and we aggregated this data in census block group level. Census block group level is the lowest spatial unit in census data, which actually have the all socio-demographic information available. Next, please. And I wanted to just give a very brief, the introduction, how the extreme gradient boosting machine learning model does work. If you are interested, I can definitely forward the main paper based on where it actually comes from. So it's actually the supervised machine learning model, and its background is definitely the decision tree, and definitely number of thousands of decision trees. And one of the fundamental, that's a good aspect of this extreme gradient boosting modeling is that it builds the trees sequentially, not in the parallel way. And each subsequent tree actually correct the errors of the previous trees to generate the final prediction to make a more improved prediction for the output. Next, please. This is our predicted air temperature, and our extreme gradient boosting model achieve a reasonable accuracy, more than 0.62. That means more than 60% accuracy from our cross-validation study. And you can see in the census block group level, I think if you can recall that, if you are familiar with the socio-demographic information, census block group level is does not have that much kind of, the defined boundary. In terms of like, it depends on the population, not in the fixed level, 1 kilometer or 2 kilometer. mostly depends on the population data. And usually the population ranges from 600 to 3,000. And in the downtown areas, is most of the we have seen most of the census block level is around 1 kilometer by 1 kilometer roughly. But some of the definitive census block has the higher area, and some also have the lower areas. Next, please. Then we wanted to, as Dr. Sailor previously mentioned, as based on the availability of the satellite data, some of the research, definitely we are not going to say that is wrong, but some people usually tend to use the surface temperature as an urban heat island as a proxy. I mean, that is certainly one aspect as a good, but as Dr. Sailor mentioned, that human exposure and the other health aspect is mostly dependent on the air temperature, and air temperature can vary from the surface temperature on the air temperature. So this is one of the example images of the land surface temperature for the Phoenix area, which have been produced with the Landsat satellite images from the last summer. Next, please. And we use this land surface temperature and our predicted air temperature, as I presented in the last second last slide. And we wanted to see how these two are correlated with a bivariate relationship. That's been, for this analysis, we are not considering other aspects, for example, the elevation, canopy cover, the development density or intensity. We are just want to focus at how the single way surface temperature can affect the air temperature. With a 3-hour lag period, based on our initial assumption that since when the surface get warmer, it not instantly warm the above air temperature. It takes time. So usually we focus on the 3-hour lag period. And based on our initial investigation, we have seen most of the areas do not have a statistical significant relation with the surface and the air temperature. Some of the areas have positive linear, and surprisingly, some of the areas also have the negative linear. And I want to emphasize that this is based on the single day and the single traverse measurement of the air temperature data. This actually supervises our traverse, which has the full scale data. In the summertime, we have taken 3 time measurement, 11 a.m., 1 p.m., and 3 p.m. So we will be able to investigate multiple lag period time so that we can have a full scale understanding how much we can, in effective way, how can we use the land surface temperature as a good proxy for air temperature for our study area, that's with the Phoenix metropolitan area. Next, please. I would like to invite Dr. Sailor again to wrap up our presentation.
All right, thank you, Alamin. Yeah, so as Alamin noted, these are only preliminary results, and our goal here was that we conducted an initial set of observations in the summer 2023 that helped inform the measurements that we took this past summer. This past summer was a very extensive data gathering campaign, and so we've established these research questions that we're interested in, but we've only been able to do sort of a cursory look at each of these questions. So these are preliminary results. However, they do lead to some useful initial conclusions. So first of all, I think we've demonstrated that cool pavements reduce subsurface, surface, and near surface air temperatures, but the performance may degrade over time as the cool surface actually becomes darker, less reflected over time. And there's also some additional questions that we can certainly talk about with respect to the diffusion of that cooling effect vertically and horizontally downwind. Water bodies in neighborhoods reduce daytime local and downwind air temperatures, but as Alamin pointed out with the literature, there are extensive or at least a number of studies that have shown that there may be a local warming effect at night. And we do have traverse data actually going from, I think earliest we did was 6 a.m. in the morning. The latest we did was 2 a.m. the next morning. So we have almost a complete 24-hour swath of data to draw upon to look at day versus nighttime effects of each of these issues that we're looking at and over time. So the urban parks, or the golf course that we tested, does reduce daytime local and downwind air temperatures. For that particular traverse that Alamin shared, we didn't have a really good upwind downwind comparison that we could make because we had a different driver in that evening than in the morning. They did a slightly different path. But again, we have a huge set 2 months worth of data to draw upon that will let us do that analysis more systematically. Atmospheric modeling is typically done at 1 kilometer resolution or higher. But our concern here, based on our initial analysis of spatial variation, is that that kind of modeling may actually mask some important subgrid variations in thermal environments. In fact, there have been a number of studies that have looked at air temperatures in a neighborhood and said, okay, here's a representative air temperature for this neighborhood. And then they classify the neighborhood, and they do this for a dozen different neighborhoods, but they have one measurement in 1 yard. And in fact, we have a simultaneous study going on where we're looking at air temperature variation even within a single land, parcel of land. So in a house's lot, if you put 6 weather stations out, you get 6 different results in terms of what the local climate is. So you have to be very careful about those sorts of questions. And then in terms of future work, most of the future work really revolves around systematically going through this huge data set that we have to strengthen our preliminary analysis and conclusions. We also intend, as Alamin said, to investigate the lag time between surface temperature and air temperature to get a stronger model to relate LST and other surface land cover characteristics to air temperature, so we can get a better model of spatial variation of air temperature throughout the entire city. As Alamin, I'm not sure if you mentioned it, but the Landsat overpass time in Phoenix is between 11 and 11:30 a.m. And so this summer, we actually made measurements at 11 a.m., at 1 p.m., 3 p.m. in the same neighborhoods on the days of the overflights. So we could actually, Landsat passes over Phoenix every 16 days approximately. So we can actually systematically look at that air versus surface temperature correlation. And then finally, to explore covariance of socio-demographic factors and air and surface temperatures across Maricopa County over a large period of time. So we can look at historical data for land surface temperatures, as well as historical data for sort of a hybrid of modeled versus and measured near surface air temperatures across the entire city for, again, for a long period of time. So we can actually look at how these factors and these relationships have changed over time. So with that, let me just conclude by saying that, again, I want to emphasize that this only represents one aspect of our heat-related work in the Southwest IFL. Our observational sites that we studied included, we had our traverse measurements, but we also had a mobile observatory from Katya Lamer at Brookhaven that I have not talked about any of those results. We also had an extensive network of stations, of weather stations, of urban flux towers, and other mobile platforms that we deployed this past summer. None of that was presented in this talk. And finally, we also have researchers looking at, like Mark Keir at University of Arizona is looking at heat-related questions in indoor environments. That's that paper in the bottom left-hand corner. And our Resilient Solutions team is working on understanding how to inform public policy and planning related to heat. So they've contributed to a number of planning documents with city partners. That's this heat action roadmap example in the top here. So with that, Alamin and I will be ready to take your questions. I think Christina wants to have the second presentation first and then Q&A, but hopefully we kept to about our 30 minutes.
Thank you, Dave and Alamin. You were perfectly on spot on the 30 minutes. So thank you very much. Nice job. Yeah, I thought that having the discussion later could actually allow for more inter IFL conversation. So now, Darryn, if you want to start with your presentation about observed heat in Baltimore, then we can move after that to Ali.
Can everyone hear me now?
Yes,
Okay, great.
you're still in presentation mode, though.
Let's. Okay. So this is good. I think there'll be some synergy about what I'm going to talk and what you've just heard. So I'm going to give half a presentation on the observational side, and then Ali will give a presentation on decision support related research. And first of all, I should say this is a large number of people who have been involved with this from a large number of organizations, including a lot of community groups. And so this is looking at heat variability in the city, trying to answer some similar kind of questions that we've just heard, trying to identify how much the heat varies within the city and at what scale, so that we can identify the communities that are vulnerable to heat and come up with equitable kind of solutions. And Baltimore, just give you a quick kind of overview of Baltimore to make sure everyone's on the same page. So Baltimore is a very segregated city. And so this is just showing the green map is the percentage African-American population. And you can see the inner harbor is at the bottom, and east of west of that, there's two regions with large percentage minority. And then there's a region to the north and the bottom that has predominantly white. And so this is referred to as the black butterfly in Baltimore. Occasionally it's the black butterfly and the white owl. And you see that in racial percentage of minority, but you see it in life expectancy, which is the inverse. So the higher life expectancy is in the area where it's predominantly white, and the reverse for the predominantly black. And this occurs for income and most socioeconomic quantities. When you plot them in Baltimore, you get the same map. And it all can be traced down to the kind of home loans and redlining. Something that might be less well known is if you look at where observations are. And so in terms of weather stations, the National Weather Service has one in Baltimore, which is at the inner harbor, and one at the airport. But over the last kind of decade, there's been a large number of citizen scientists who buy their own weather stations, where they're hobbyists. And so now they have a large percentage of those. And the black dots on this map is showing where there are these weather stations. This one's from the Weather Underground collection. And so it looks like there's a really good collection of weather stations, except if you look a little bit closer, you actually see the white owl comes up and where there are weather stations in the city. And there's very few, if any, in these areas with low income or high minority. And these are where we think the vulnerable populations live. And here we don't have any measurements. And the same pattern, there's a citizen science network of rain gauges. If you look at that, you see the same kind of gaps in the low income neighborhoods. And so for BSEC, we want to kind of address that and try and map what the heat is and understand kind of what causes the variability and how we can change it. I'm going to focus as the last talk on air temperature, so I'm not going to talk anything about land surface or median radiant temperature. We can come back to that in discussion. There have been previous efforts to try and map it in Baltimore. Hopkins Group have been involved with putting out small, low-cost eye-button sensors in trees and then using machine learning to form a map of the temperature. This is an anomaly. And there's also been a NOAA vehicle transect, which did, on one day, went through and did 3 different times of the day. And so you can map those together and get a map of what the kind of heat or temperature looks like. there's some limits on what you can do with these, and there's and so the approach that we've taken is to look at expanding the number of weather stations that are in the city, partly because of the heat, but also partly because this provides information on rain, and flooding is one of the key focus of BSEC. And we also get wind and solar radiation, which will be useful for understanding the cause of the temperature variation. I don't think I need to go into the details, but we've got 10 kind of research grade weather stations, and then we've currently got around 30 of these personal weather stations that we're deploying. And we've been doing this, leveraging a lot on our community partners and growing partners through this. And so we have these weather stations at a lot of different kind of environments, faith-based centers, community gardens, private residents. And so there's a lot of interactions with a lot of people. You'll also see that the sighting of some of these is less than perfect. That's part of the advantage, but part of the challenge of this network is we have got these weather stations either too close to buildings or close to trees, in the very type of kind of environment that you get in a city. Sorry, what's happening there? So this is the current location. So the red dots are where we've added in weather stations to the existing weather underground. It's not very evenly spread out. It's been somewhat systematic, but somewhat community partner based, and identifying someone who's interested in hosting them. We also have a large number around Broadway East area over here, the East Baltimore, where our key partners are. And part of this is also trying to identify, well, how many weather stations do we need in a small area to characterize the temperature? And just, I'll quickly go over this. So if you look at the weather underground and looked at where their weather stations are relative to income or percentage non-Hispanic blacks, over 70% of the weather underground were in the very high income and low percentage black. The red is where we've put stations, and so we've ended up being a little bit more even, and certainly have a lot more coverage in the low income, high minority neighborhoods. Okay, so this is just again very preliminary results, and in fact most of the results are going to be shown from the work that undergraduates have done over the summer. So the first thing that's come out of this is just the BSEC weather stations. So we have now data that we can map out during heat waves. The left plot is the minimum temperature on the 6th of July, and the right one is the maximum temperature. And you see hotter in a city, cooler as you go out, and the difference is around 7 to 9 kind of Fahrenheit. You see that for the minimum and the maximum temperature, but I think you'd argue that the minimum, the dawn temperature shows a much smoother kind of transition, where the daytime maximum, there's some rural stations that's nearly as hot as the inner city, and there's one in the inner city which is quite a bit cooler. So there's extra variability in the maximum temperature. Another way to look at that is to plot for each day, or these are 3 different days, the maximum temperature versus the minimum temperature on that day for each station. I'm not sure if this plot labels are pretty small. These are 3 different days. Doesn't matter which day, there is a correlation. So there's a tendency for locations that have a hotter T-min have a hotter T-max. But there's a lot of spread. And in fact, there's very few locations that ever have very high T-min and very high T-max. So all these stations up here that have high daytime temperature have average to below average minimum temperature. So they've been controlled by kind of different factors. And you can see that another way by plotting the regression of the daytime minimum temperature versus NDVI, which is a measure of greenness, and the maximum temperature. So for the nighttime temperature, there is this weak negative relationship. So the greener the environment, the lower the temperature. You don't see that for the daytime maximum temperature. There's basically no relationship at all. And to try and get to the bottom of that and some other curious results we've been deploying 4 to 8 sensors around various weather stations, usually just for a week or so we can sample the different environments. And this is just 3 of the sites that we've done. And there's a fairly common kind of response that so these are plots average over, say, a week's worth of data versus time of day. So this is like 6 or 7 a.m. is when there's the minimum. And that doesn't seem to depend on, the different color is just a different sensor, but within around 30 meters. And the minimum temperature varies only weekly. However, if you go to the daytime maximum temperature, you're getting this range of 2 to 3 degrees Celsius within a very small region. So it's very reassuring that that number is the same ballpark number that we just heard of from the Phoenix studies. And so you get a range. You also get a variation in exactly when the peak is occurring. And so this is due to where stations are relative to shade or other kind of factors. And just another, I should say that we've talked about, focused on the heat variability, but all I've talked about is air temperature. The relative humidity also varies within the environment, but if you convert it in, most of that comes from the temperature variation. And this holds for eye buttons. It also holds for the weather stations, that if you actually looked at the water vapor mixing ratio, its spatial variation is much weaker. And so if you calculate a heat index, 90% of that variation comes from the variation in temperature, either directly or through the relative humidity. I'm just going to step back. I should say that these results all here from weather stations, but in previous years, we've put these eye buttons out and got exactly the same result, that depending on where you are, you can get up, in that case, it was up to 4 degrees temperature difference. And so I think that this sensitivity to the small scale is part of the reason why we're not seeing the strong signal with this larger scale kind of NDVI, and why Tmin and Tmax aren't perfectly correlated. Okay, so that was all I had on the observational side. This is all preliminary work, and we've got lots of work to quantify this variability and then be able to kind of isolate it. And then one of the key things we want to do is evaluate our dynamical models and then feed it into decision support models, which you're just going to hear about now. And that's all I have. So I'll stop sharing. And Ali, you can take over.
All right. Can you see my screen?
Yep. It's not full screen yet. Now it is.
Okay, thanks there. All right, so hello everyone. My name is Ali. I'm a PhD student at Hopkins, and this presentation is going to be about urban adaptation and equitable urban heat island reduction pathways under climate change. So I'm going to start with like a general definition of urban adaptation. So it's basically the process of adapting our cities to various outcomes of climate change. And we do this using different methods like developing green spaces, building resilient structures, and so on and so forth. But planning for this future can be quite challenging. There are a lot of important things that we need to consider, like how is this future going to look like? How much can we afford to pay? How can we make sure our solutions are equitable? What goals and objectives do we have? And how do we know if this is even going to actually work out? So generally in these kinds of environments, we can have different levels of uncertainty. So in general, we can make our decisions either under complete certainty, where we exactly know what the consequence of each alternative going to be, or it's going to be under risk when we don't know exactly what's going to happen, but we know the probability of different outcomes. Or finally, and as is going to be the case for most urban adaptation research, we decide under deep uncertainty, where we don't know what's going to happen and we don't know what's the chances of different things happening are going to be. Here we can see these differences in more detail in terms of context and different problem structuring. We basically can go from a complete certainty where we know about the future to total ignorance, where relatively little information we're going to have about different aspects of our problem. So there are different ways to tackle decision-making for an issue like urban adaptation. What I want to focus on here is many objective, robust decision-making. So, or MORDM. So MORDM works on problems that involve multiple criteria and tries to structure them and find solutions for them. But in these kinds of problems, there isn't usually one solution present. And we have to look at trade-offs between different ones. And we usually do this through multi-objective optimization. In this picture here on the right, you can see how this is an iterative process and the different components of it, going from things like problem formulation to trade-off analysis, and so on. And that brings us to what this study is about. What we are trying to do is basically mitigate the outcome of extreme heat in Baltimore, which is worsening throughout the years because of urban heat island. And what I focus on is heat-related mortality, which is a major issue, as Baltimore in recent years is having a big portion of the deaths compared to the other areas of the state. And the question is, what are some of the strategies we can use to achieve this? Here I want to focus on 4 different ways we can use to counter these effects. Strategies that are shown here are representing planting trees, implementing cool roofs and cool pavements, and using cooling centers. So each of these have proven to be useful in different extents and for different specific purposes. And they can also be quite different in terms of their cost of installations and maintenance, and also their effectiveness. All right, so to summarize, until here, we're trying to provide cost-effective policies for urban adaptation while considering future conditions and uncertainties. And how we want to tackle this is by building an adaptive and dynamic framework to evaluate the policies while considering these deep uncertainties. And the framework we are going to use, we are using is called City Heat. So it was a framework that was developed here at Hopkins a few years ago. And what it does is basically identifying strategies to counter urban heat waves and reduce vulnerability under uncertainty and many objectives. And it does it in an adaptive way, so the plan can be responsive to the environmental conditions. And basically the pathways for doing this that we develop are at community statistical area level, or CSAs, which we have around 55 of them in Baltimore. And the model uses several metrics to do this. So here on the right, you can see some of these metrics and how they differ. And these are basically some of the general inputs of the model. So some other informations about the details of it. In general, what this model tries to do again is to reduce heat-related mortality and increase equity while spending money in a reasonable manner. And it uses different strategies to achieve this. Again, like greening, implementing cool roofs and cool pavements and cooling centers. It provides policies and plans for each community statistical area for the next 50 years. And there are, as I mentioned, several different uncertainties included here, which are things like actual effects of mitigation strategies on temperature, the rate of temperature increase itself, and the relationship between temperature and mortality, and so on and so forth. Okay, let's see now how this model actually works. It's a pretty straightforward optimization simulation framework. What we have here on the left are the inputs of the model, basically the decision that we are trying to make, which are the strategies that I talked about. So let's say we choose a certain pathway of these strategies. which is the plan in different regions of the city. Then we evaluate this plan under a quite big number of scenarios that come from our different uncertainties that we have to see how well this plan performs in terms of 5 different objectives that you see here on the right. And this whole process gets basically repeated multiple times inside an evolutionary algorithm and until we find our final plans or pathways. But as I mentioned before, for these kinds of complicated problems, there is no single unique solution. What we'll have instead is a set of solutions that each perform relatively well, and then we will look at the trade-offs between them in terms of what our objective values look like. And then we might be able to pick between them based on how much importance or weight we put on each of our goals. So having said this, running a model like this would result in this kind of representation of the solution space. So each of the lines in the plot on the top show one adaptive pathway and how it's performing in each of our 5 objectives that you can see there. We can see the trade-offs between these solutions and what we would expect to happen on average in the future if we decide to choose them. And these are values. The values of the objectives that are shown here are for using these plans for the next 50 years. And you can see the direction of preference or where we would want our objective values to be. And at the bottom 2 plots, the bottom 2 plots also show the trade-offs between pairs of objectives out of all the 5. Here we see the relationship between mortality reduction and cost, and also mortality reduction and equity. And each of these dots on the scatter plot again represent a specific adaptive pathway. And here again, we can see the stars show us where in the plots we want to be. We also selected 4 representative pathways here, so we can look at their details later on. The pathways are basically focused on either greening or infrastructure, or are doing like focusing on all different strategies, or like focusing moderately on all of the strategies. So one interesting note here is that higher spending, especially in the case of greening strategy, doesn't always reduce inequity. So one reason for this could be the lack of planting sites in the urban core in Baltimore compared to the infrastructure possibility. And even though equity is one of the objectives of the model, the mortality reduction in the older but at the same time richer neighborhoods puts these kinds of pathways in the solution space. And so this kind of results highlights how important it is to look at the trade-offs and also like gather community insight when developing and providing these kind of policies. So for these 4 pathways, we can look at different metrics and how they change through time. Here we see cost, mortality, number of heat wave days, and Gini index, which is another measure of equity that we use throughout the simulation years averaged over all our scenarios. And we can see here how that, as is the nature of adaptation strategies, the upfront cost is quite high. And also we can see again how the expensive solutions aren't performing quite well in terms of our equity metrics. And we can also map these metrics out. Here we have the total investment for our pathways in neighborhoods. Again, we see the discrepancy between the investment size in these 4 representative pathways. So the tree-dominated strategy does invest less in underserved neighborhoods, while the infrastructure-focused strategy focuses more towards poorer neighborhoods. And this again confirms the equity-related results we found previously. And finally, to see how these investments look like for all neighborhoods, here we can see a heat map of dollars spent each year for the greening pathway as an example, and how selective again it can be in terms of location choice and how it changes as time goes by throughout the 50 years in different CSAs that we have. All right, so to conclude, we saw how our framework can be useful and can function, and also how subjective it can be to the selection of objectives and interventions. And also the importance of equity metric is quite clear, and we are trying to optimize the model with alternative ones. And we can see how the results are still not quite actionable, which does highlight the necessity of a detailed discussion with decision makers and stakeholders. Okay, thank you.
Thank you very much. And very, very interesting presentations. I'm sure they have spurred a lot of thoughts across all the IFLs. I see a lot of really important touch points. I can see how we can develop papers together, meta studies of heat in urban systems. Unfortunately, the other two IFLs are not presenting today, but I look forward to these. So we have a little more time. We have about half an hour at this point for questions. And so anybody who would like to start with questions. Ben.
This is for Ali. Very nice presentation. Question I had is, have you been thinking about or looking at the air quality impacts of widening roofs or adding more vegetation? Because with a wider roof, you're going to be causing more radiation to bounce back, which could potentially increase photochemistry and lead to more ozone or secondary organic aerosol. And with adding more green trees, that can also be adding to ozone or secondary organic aerosol. So have you been thinking about that, or is that something that we should be talking about since I'm also at Johns Hopkins? Thanks.
Yeah, thanks, Ben. So I have not. The model right now is just like basically focusing on heat-related mortality. So that's like the basic. It has like CO2 reduction as one of the co-benefits, but it's not like that detailed in terms of how it calculates it. But absolutely, like the changing the objectives of the model and just like fine-tuning them has been like one of the things that we've talked about. But yeah, definitely that's quite interesting.
Definitely, that goes towards the total assessment of the feedbacks to the climate system and the urban system. Other questions? People, don't be shy. I don't see anybody here.
So I could just add a little bit on that last question from Ben, perhaps. So I don't have it in front of me, so I can't speak to this exactly. But in terms of the reflection of radiation that could then affect photochemistry, sort of double whammy effect. I believe that most solar reflective surfaces do not have increased reflectance in the UV spectrum. And so I think for the most part, it's increased reflectance in the visible and near infrared. So I think it has less of an effect on photochemistry than you might think. But that's just as I recall it. So just thought I'd throw that out there.
I need to look at some of the photochemical species because, yeah, that won't impact ozone, for example. That might still impact carbonyls. I forget exactly where they undergo photodissociation, but it could still have some impact that I want to look at just to confirm what I'm thinking.
Which brings me to a question that says that really still for Ali. I really enjoyed your presentation a lot about the working under deep uncertainty. I was wondering if you were to project out which is the major source of uncertainty and under these decisions, what would that be, or what is the priority for that? Also, in my mind, it really depends on how wide a cast you want. What wider net you want to cast. In other words, the type of effects that Ben was mentioning or others, those be parts of this multi-factor optimization and trade-off approach?
Yeah, so by far the most important one and the most obvious one is like the temperature projections for the future, right? So there are generally like two types. There are types of uncertainty that they are uncertainty because we don't have enough information in terms of, or we haven't done enough studies in Baltimore in terms of, what is the effect of like planting trees on temperature exactly, or like if we do plant trees, what's going to happen to like mortality, heat-related mortality. But I have done like quite a simple sensitivity analysis on like how the results changes compared to like based on like the uncertainties, and like the temperature projection like dominates everything else, like by far, because of how wide ranging it can be.
Thank you. Anybody else has questions? Don't be shy. Otherwise, I have another question. I was wondering, and this is a question for all of the speakers, where do you see and what is the most important contribution of community input into your studies, and how have they shaped, were you able to translate information? What type of information are you seeking from community? How do you translate that into knowledge that allows you to refine your approach or your science questions, or the way you go about them?
Maybe the silence speaks to some of the challenge there, Christina.
Yes.
So, one thing that we've been trying to do in the Southwest IFL is, I think as is the case with all the IFLs, we wrote well, at least I can speak for ourselves. We wrote our proposal largely focused around research questions that academicians came up with. And the vision was to then integrate stakeholder input over time and have those questions evolve. And so we've been trying to do that through our stakeholder engagement at our all hands meeting, for example, and then also through our stakeholder advisory groups. And the types of questions that that stakeholders care about, a lot of it focuses on data to guide decision making. At least that's both for individuals, but especially for local governments. They want data to inform their decision-making processes. They want information on cost-benefit analyses, that sort of thing. And so that is reshaping how we're thinking about some of our science questions, but I'd say we're still evolving to meet them in the middle.
Thank you.
And from the BSEC side, I think there's some similarity there. One thing that's happened in terms of the weather stations and trying to find community hosts has started kind of a dialogue between a variety of different kind of community groups about not only what they want, what kind of education or community outreach do they want to do in their own community. So there's been the people that I'll meet in the community are some community leader. They're kind of aware of the environmental issues, and they're looking for help to actually educate their own and empower their own community. And so that's slightly different from us focusing on the question we want to answer, but it's kind of one of the things that we've encountered, that they're aware of the challenges they have. But a lot of the people who live in their community aren't as aware of the environmental issues. And so they're looking for a way to kind of help do that education and then empower the community with the data and things like that. And so in fact, the weather stations, we're now putting some of them out, driven more by that community desire to have their own information than necessarily we need that data for our science.
Thank you. Anybody else has any questions? We have a lot of time.
Well, I was just speaking, I'll ask you a question from the other Alamin. In terms of this correlation between the surface temperature, land surface temperature, and the air temperature, I got a little bit. Is that the temporal correlation that you're looking at, as opposed to kind of the spatial correlation if you're wanting to see which regions are hotter or cooler?
If I get it correctly as your query, so there's a single time frame data. For example, Landsat usually pass around the 11 a.m. at the local time, And we also had the air temperature measurement around 2 p.m. with the traverse data for the single day. And we wanted to see that how the spatial variation, not the temporal variation. I want to make it clear. And this is the only as I mentioned that is the if the temperature is from 11 and the surface temperature from 11 and the air temperature from 2 p.m. So it's around 3-hour lag period. So that was the one of our assumption, like we are thinking we might get kind of a signal from there. So that was our last year data. And this actually guided us to make extensive measurement in this year where we have data from on 11, 1, and 3 p.m. That's been 3 lag periods. So I believe we will be able to get kind of more insight on that, how this kind of variation is happening in the Phoenix. It's a desert setting area. And like for this relation, that was only just how the land surface and the air temperature is correlated, or is there any kind of relation with them, whether it's positive, convex, or concave. But we did not actually get the chance to explore the other. We did not consider the other variables. For example, yeah, temperature. Certainly you would agree that the development density or the intensity, like the building height, as well as the impervious surface coverage, vegetation height, all are actually affecting that. So one of the hypotheses was that, like, if we don't consider the other variables, and if we just say about that, is this land surface, surface temperature is higher is here, so that's mean it has a higher urban heat island, we might be a little bit misleading, making some kind of conclusion. We have to consider the other variables which actually have the real, the impact, which can influence the air temperature, because surface temperature usually depends on the I would say the sky view factor and the solar radiation and the other aspect, definitely elevation. But when it's actually surface got warmer, it started to warming the air above the air. So and then other and the neighborhood factors actually come into the play. So that was one of our the initial hypothesis on that. I'm not sure whether did I answer your questions.
Yes, thanks.
Thank you. Thank you.
Thank you. Anybody else?
I'm sorry. I really enjoyed the presentation. The Ali was discussing is very amazing, and I'm not sure. Like, I just want to learn from him. Like, he's focusing definitely on the heat-related mortality. So, if I get it correctly, so you are getting this information from how we will get the heat-related mortality. So how we can quantify that, or what is the source of the data? I just want to learn from you so that I can also use that in my research too.
Yeah, sure. So for that, we really do not have data for Baltimore. At least I haven't had. So it has been done based on studies from other cities, like from Chicago or from other places, and then we basically pick it as one of the uncertainties of the model, and we say, oh, there's 4 different outcomes that can happen if a heat wave day happens. We can have this kind of relationship with mortality, or the other kind of relationship with mortality, and it's basically a range of effects that heat can have on mortality, and we basically pick and choose between them and average all of them. So that's how we basically define how the relationship between temperature and mortality is going to be as one of the uncertainties of the model inside our scenarios. But yeah, data that
that's actually that's actually coming to my mind. If you definitely there are existing literature, I think you have already learned that. So when it comes to the mortality related to the heat, definitely the air pollution and the air quality also have the impact. It's kind of joint effects. So are you considering that effect, or you I don't know, are you thinking about that to exclude the effect of the air pollution, or just it will be the combined, the joint effect? How do you think about that?
Right now it's only temperature. Yeah, it is just temperature, but that could be quite interesting to just add. Yeah, for sure.
Okay.
Yeah.
Thank you.
And I was just going to add that, so in Maricopa County, we actually have very good heat-related mortality data from Maricopa County Health Department. whether the incident was indoors versus outdoors and so forth. But one thing that's interesting from our data that makes it, I think, hard to, hard to move forward with some of these models is that there are so many other factors that drive heat-related mortality, and a lot of it has to do with, support for homeless services, as well as drug epidemics and so forth. And so you can look through our past data and find a particular year where the mortality increased, but the temperature decreased, or vice versa, right? So there's a lot of complexity in there that we just have to tease out, and that's from a non-health researcher.
So I have one question for David. Dave, are you planning, how frequently are you going to run? Is every summer going to be a time for having another campaign for the duration of the IFL?
Yeah, since our IFL is very much focused on heat and heat-related environmental concerns, so we do focus on air quality. And in fact, Alamin's doing some work kind of similar to what BSEC presented, but focused on air quality data and purple air sensors and EPA site locations. But because our focus is on heat, our field campaigns are each summer, at least through the 4th summer. We'll see about the 5th summer. But so next summer we'll have another campaign. We'll learn from this campaign. It's interesting because Katja Lehmer brought her two mobile observatories here, and when I candidly asked her, so how long do you think it'll take you to analyze the data? She said, oh, maybe 18 months for a campaign of this size. And we're going to have another campaign in 12 months. So we're going to have to figure out how to really go through this tremendous resource of data. It's important that we do it in a timely fashion because it helps to inform what we do next year. And so that's why I wanted to quickly share, some of our initial results from this summer before we have, because it's going to take us months to actually do a thorough analysis. But this gives you a flavor of what we're finding. And I found it very interesting that BSEC is seeing very similar sort of microclimate variability that really brings into question, many, many, many studies that have happened over, in the past years, where we get a representative measure for a neighborhood based on one station placed in someone's backyard. And if they happen to have a swimming pool, or if it happens to be near the air conditioner, wherever you place it matters, right? And so seeing that their variation, on the scale of 30 meters, we certainly have variation finer scale than 30 meters or than 100 meters, but ours showing 100 meter, significant variation, 2 to 3 degrees C. I think there's a lot that we can do to explore the implications of that, and maybe there's some collaborative work to go on between the two centers even.
I totally agree. I think the crux of the matter is when you deploy some instrument or some measurements, or if you go about what the error included in what that observational unit samples is really critical. The moment we have actually teased that down, we will have really understood a lot about how to do science in the city in such a heterogeneous environment.
Right.
Really.
Right. And we're also trying to combine diverse data sets. So most of the weather stations that we have access to are not aspirated, but there's clear evidence that a non-aspirated sensor, even in a really nice radiation shield, you're going to have a temperature bias on a hot summer day of 2-3 degrees C just because of that, right? And so that's why our traverse measurements are self-aspirated, so that helps there, but they have their own challenges because they're in the middle of the street, not in people's yards. And anyway, so there's no perfect measurement, I think, is the upshot.
I think that would be a wonderful opportunity to really gather the 4 IFLs and thinking about that particular topic. How do we know that what we're measuring is representative of what we want to measure? So. All right, any other questions from anybody?
It's not a question, I'll just add a follow on. So we agree with everything that David just said, and we've hoping in the next couple of weeks do a few preliminary bike. So we've got a bike set up with a temperature sensor on it. So Ali's smirking because he's going to be the one doing all of the cycling, but we're hoping to use that to test out. So next summer we can maybe have more of them. And again, we've gone for the bike rather than the car because we want to be able to transverse across some of these parks or wooded areas. And it's cheaper.
Yeah.
But already I can see the data that's going to come out of that. It's going to take a long time to analyze.
Yes. Indeed. Last call for questions. If not, if there's no other questions, I can give you back 10 minutes of your daily calendar to do other things, and stay tuned for the next IFL seminar. I think these are very, very valuable, I think, to keep all of us up to date. So looking forward to that. And if it's not earlier, I'll see many of you at the Urban IFL PI meeting in DC. Thank you, everyone.
Thank you.
Thank you.
Bye.